two-dimensional problem. We'll solve it with a really simple formula. And then we'll go into 3 dimensions where you actually have to use all the satellites at some point in the Earth station latitudes and longitudes. That is a tricky problem. Take good notes because it's not in your book. I think that elevation calculation, ultimately what we're after is azimuth and elevation. They just need an elevation calculation. But I don't think they have the azimuth calculation included. And there's some nuances that they don't talk about either. So this may seem like simple geometry, but it actually gets very hairy. So pay attention. Here's our problem. The Earth, radius of the Earth. What is the radius of the Earth? Here's a nice precise value down to the kilometers. 6,378 kilometers. What about mean Earth radius? We said earlier that the Earth is a oblate spheroid. Depending on where you go in the Earth, it could be a few hundreds of meters off. And let's see. Radius of the Earth. Here's our Earth station. Here's our satellite subpoint. Here's our radius of the satellite. Here's our satellite subpoint. Here's our satellite. The centroid of the Earth station, and the satellite make a convenient triangle. And if you can imagine, what is it that we're trying to guess in this two-dimensional problem? Well, in this 2D problem, what we really want is elevation. If I'm an observer standing there on the surface of the Earth, the tangent line that I just drew, the dotted line, is sort of like, that would be what an intercept, a plane that is tangent to the surface of the Earth, and where you're standing would bisect this diagram. We're going to split it, come out of the board, and shear it tangent to the surface of the Earth. And that would represent the upper hemisphere that is actually visible from an observer on the Earth. In other words, if this satellite were to drop below this dotted line, it would no longer be visible, right? And this essentially is 0 degrees of elevation. 0 degrees of elevation is right along the horizon. We're going to measure elevation in this class as a function of degrees away from that horizon line. Now keep in mind that's different than the mathematicians, how they taught you to measure elevation in the electrical engineers that taught your E-Ray class. They're teaching you elevation from the z-axis. This is 0 degrees, and then you go down this way to 90 and 180, etc. So just recognize that a lot of the formulas that you'll see for elevation in your math textbook, you got to massage them a little bit to make it into a book angle. Okay, so this is the angle that we're after. E, we'll call it E little l. L. Okay. So, to figure this out, it's actually very simple. I won't derive it on the board. It takes too long. You can probably do it at home. But it's basically the law of sines, the law of cosines. You remember those from your trigonometry days? And so the cosine of that elevation angle is equal to, okay, in order to figure this out, I need to figure out what this angle is. Gamma. The subtending angle. This means the Earth station, the center of the Earth, and the satellite subpoint. The angle formed by those two line segments. And if I have that, then I take the sine of that gamma, and I divide it by the square root of 1 plus RE over RS squared minus 2RE over RS cosine gamma. So if I know this angle, to the radius of the Earth and the radius of my satellite, I'm in good shape. I can actually calculate the elevation angle in degrees by just taking the arc cosine of this. Now, this is a general formula. If you want to do this calculation on another planet, you want to figure out what the elevation is of Mars, you just put the radius of Mars here, and then use the radius from the centroid of Mars as our so that's it's a generic mathematical formula that will work for anything. But it is in 2 dimensions. Now, we're going to use this for our 3-dimensional formula. Our 3-dimensional formula is basically just going to add another step. You might every 3-dimensional problem, if you slice it right, is a 2-dimensional problem. If I take a slicing plane that contains the radius, the centroid of the Earth station, and the satellite subpoint, I will slice that 3D problem, and it will look like, in a cross-section, it will look exactly like this. And so our pre-step, I'm not going to put it on just yet, I want to show you something else first, but our pre-step to the 3-dimensional problem is using our satellite subpoint and Earth station longitudes and latitudes to calculate gamma before we do this calculation. And then we move off into azimuth calculations. Okay, now, any good engineer trying to calculate an elevation angle will do one important test first. It's called the visibility test. You calculate gamma, and if gamma is less than or equal to the arc cosine of RE over RS, then the elevation angle is visible. It has not dropped below the horizons. So this isn't the final ultimate test of visibility. These are a lot of other factors that play into visibility. mountains could get in the way, buildings and trees could get in the way and obstruct things. Your spacecraft could be optically visible or at least line of sight visible in terms if you ray trace the path, but down on the horizon there may be too much atmospheric attenuation in your signal to actually see the satellite that would otherwise be audible if it was overhead. So this is really just a geometrical visibility test. If I lived on a flat Earth out in the desert, is my satellite going to be above or below the horizon? If it's below the horizon, it doesn't matter how many mountains or what terrain you have, it's not going to be visible. And this is a good test to do, especially when you write code for your homework, because students get in trouble a lot of times with these assignments because they start to get nonsensical answers. So, for example, they'll graph elevation and azimuth. In this case, elevation goes from 0 to 90 degrees. 90 degrees is straight overhead, 0 is somewhere on the horizon. And then azimuth is 0 to 360 degrees, somewhere along here. And they'll give me a plot of a sky track of a satellite where it's evolving over time in the sky, where you have to take your dish and track it around. And sometimes you'll see some crazy things like this. The satellite will do this. That is one messed up spacecraft. Right? It would appear to something like this, and if you put like a conditional statement for visibility in there, you'll get rid of all these points, which are actually somewhere below the horizon, giving nonsense results. So yeah, always be wary when you show me code of Skytrax that just like suddenly bounce for no reason. Think about that. It takes a tremendous amount of rocket fuel to suddenly reverse like that. It's okay if there's like a little fuck there, but that just means that the Earth's spinning and the satellite is doing its crazy inclined elliptical orbit. It's just maybe in some sort of peculiar place where it's accelerating it a little bit faster, then a little bit slower, than the Earth's rotation at a given point kind of moves around. That's permissible. For no points that bounce. Okay. Now, to extend this to 3 dimensions, there's a very simple formula. Calculation of that subtending gamma angle for 3D. The cosine of that gamma is equal to sine L sub S sine L sub E plus cosine L sub S. Now look at my notes, make sure I don't mess this up. Too dangerous to do it from memory. This is too important of a formula. And there we have it. Now, what are the LS's and the LE's? Capital LS is the latitude of the satellite subpoint. Little ls is the longitude. And likewise, capital L sub E and little L sub E is the lat long for the Earth station. And so if you plug your latitude and longitude for satellite subpoint and Earth station in here, take the arc cosine of that, you'll get the gamma that we used in our original 2-dimensional problem. Now, don't worry if the math is getting out of hand because we've got to do azimuth. It turns out azimuth is even tougher than elevation. I'll do an example, like a numerical example with some real values to kind of show you how this all works by putting all the pieces together. Okay. Now, how do we do azimuth? This is also a 2-step process. We need an upper azimuth variable, which by convention in this class we call alpha. And alpha in this case is the arc sine of the sine of your longitude of your Earth station minus the longitude of your satellite subpoint. Take the absolute value and then the sine. Multiply that by the cosine of the latitude of your satellite subpoint divided by the sine of your gamma. So you really need to calculate elevation first because we use that helper variable in this formula to simplify it. And you're not done yet. This gives you a number that kind of describes alpha, but you'll need to make some adjustments because of the ambiguity in 360 degrees in trying to make this calculation. First of all, when we measure alpha, what are we measuring? Or when we measure azimuth, what are we measuring? We're measuring the angle that you steer something along the horizon perpendicular to elevation in order to sight in your antenna. Where do we measure it from? Well, again, here's a case where we differ from mathematicians and engineers. We use the cartographer's convention for azimuth, and that's where north is 0 degrees, and east is 90 degrees. So we are increasing in azimuth clockwise, looking down from above. So on your north, south, east, west. This is 0 degrees, increasing azimuth increases in this direction clockwise until you get to 360 degrees where it repeats over here. That's of course very different than the Cartesian coordinate system where we usually take this x-axis to be 0 and then we measure the angle of azimuth counterclockwise in that direction. Why that convention happened, I don't know. That's usually what cartographers and math people, geography people do. And so we point the dish with that type of terminology. Yes? So this is actually looking down from above, right? And if you imagine if you had an Earth station here and you looked at a compass, you have clarification of the diagram. You just looked at a compass, you have a north, a south, and an east, and a west. And so the azimuth tells you where along that compass bearing should I actually point the dish antenna. So we need to make some correction factors to get the actual azimuth. And there's a second step, which is an adjustment step. This is trickier than it looks. So put this table in your notes. The SSB, the satellite subpoint, is southwest of the Earth station. In other words, if I go to this diagram over here, this is my Earth station. I'm standing on the board. I'm looking down at somebody standing on the board or a dish mounted on the surface of the Earth like this. Southwest would mean that my satellite subpoint is somewhere in this quadrant. And if that's the case, then my actual azimuth is 180 degrees plus the alpha that I calculate with that formula. If instead the satellite subpoint is southeast of the Earth station, the azimuth is 180 degrees minus the alpha I calculate with that formula. If it is northwest of the Earth station, then my azimuth angle is 360 degrees minus the alpha that I calculate with that formula. And if it is finally northeast of the Earth station, the azimuth angle is actually just the alpha, the value that I calculate with that formula. We're not done yet. I have to make one more clarification before we apply these formulas. This conditional statement wasn't hard enough to code up. I have to be a little bit careful about how I actually calculate southwest, southeast, northeast, northwest. I have to figure out, is the satellite subpoint north or south, east or west of a given Earth station point? Well, the east and west calculation is very easy to make, right? And the reason why it's easy to make is because the longitude lines themselves bisect the Earth, right? If I take a longitude line, it slices the Earth right down the middle into two equal halves of a sphere in ideal practice, right? It doesn't matter which longitude line I pick to do that. And so, really, that part's actually really easy. If the longitude of the satellite subpoint is less than, within 180 degrees less than the Earth station point, then I'm clearly east. And I'm either going to be this condition or this condition. If the satellite subpoint is greater than the Earth station longitude, without wrapping around 180 degrees, then I'm clearly west of the Earth station. Okay, that's pretty simple to get. It gets a little more complicated. You can't do that same conditional test with pure latitude lines, because except for at the equator, the latitude lines do not bisect the Earth. If you're not cutting it into a perfect sphere. At the equator, if you have a North Pole and a South Pole, we're looking from the side, here's the equator. Yeah, latitude 0 line slices the Earth in half. But if I'm up here at the poles, and a high latitude like 80 degrees or 70 degrees, I just have a tiny little bit of Earth up here. Huge amounts of Earth right here. What I really need to determine whether something is in the northeast quadrant, the northwest quadrant, the southeast quadrant, the southwest quadrant, is a bisecting line test for this. So that doesn't look like, what I'm really saying is if something is north, then it's going to be in this hemisphere. And if something is south, it's going to be in this hemisphere relative to my observation of the Earth sphere. How is that possible? Look, you just do a tremendous amount of the north part in the southern hemisphere. Well, imagine, if you will, if I'm sitting here on the Earth, let's say this is south, and this is north, and this is east, and this is west. Okay, if I want to figure out east and west, I draw a line like this way. Let's say I had shot laser beams that could take around the Earth with my fingers, and I lined it perfectly with north and south. Let's go around and I come around and mark this perfect set of hemispheres that I could divide into east and west. Now, if I did the same thing here, the laser beams would bend around the Earth, but they would do so in this fashion. They would start out like this, and then they would bend around the Earth and bisect it in half. And so even though the satellite subpoint might be down here close. It's clearly well below this line. The latitude can be very far below that line, but it's still north relative to that bisection test. So mathematically, how do we make that bisection test? That's the key. And so north corresponds to the tangent of the latitude of the Earth station times the cosine of the differences between longitudes of the satellite subpoint and the Earth station. If that is less than the tangent of the latitude of the satellite subpoint, then you're north. If you reverse this condition, then you are quote-unquote south. And all of these tests will work out. This can be a maddening error when you actually code up and calculate things, because, especially if you pick a satellite that spends a lot of time near the equator, for low satellite subpoints and low Earth stations that are close to the equator, this test, just testing the outright latitude lines, actually is a pretty good estimate of whether the satellite subpoint is north or south of the Earth station. It gets a little bit hairy kind of around the equator, but you can run a Skytrack simulation and it almost looks perfect. But as things start to get higher and higher in latitude, you'll get these kind of quirky looking Skytracks where there'll be a little hitch in it. You say, well, where did that come from? It's probably an incorrect code. It's not doing the north-south test correctly for the azimuth calculation of the decimal. So just be on the lookout for that. Okay. Now, this is the part where we get to do an example. What we're going to do is trace an Earth station on the top of Van Leer and figure out where to point it to get to a geostationary Earth orbit satellite. So here's our formal problem statement. Earth station in Atlanta on the roof of Van Leer, which we just said was 33.7758 degrees latitude and negative 84.3973 degrees longitude. We have a geostationary Earth orbit satellite that is hovering synchronous with a sidereal day so that it never changes its satellite subpoint latitude. It's always at negative 105.0 degrees. If it was 105 degrees west of Greenwich. So, what are the look angles? That would be in azimuth and elevation. But this satellite, or this Earth station, should dial up with an antenna to point it towards the satellite. Okay. So, first a couple supplemental pieces of information. We'll give these physical constants. RE, radius of the Earth, 6,378 kilometers. The RS is the value that we calculated earlier in class. We said this is a geostationary Earth orbit. You know that that's a circular orbit with a magic radius of 42,164 kilometers. And the satellite subpoint is zero because it has to be zero. There can be no inclination for a geostationary Earth orbit satellite. And of course we said that it always hovers at the 105.0 degree longitude line. So we got our two latitudes and longitudes. Got our radii. Let's see if we can calculate this. So step one. And I'm going to put the formulas down in the form that I put them in, that I entered in the numbers on the calculator. I'll give you the results. We won't work through all the numerical detail. You can double check it at home. It'll be a nice template for your own problems, just to verify that your codes are running or that you typed in a formula in Mathematica or MATLAB correctly. Okay. Step one. Calculate gamma. Gamma is equal to arc cosine. Sine LS, sine LE, cosine LS, cosine LE, times the cosine of the difference between the longitude points. And if you do that for the numbers we got there, I've got all my longitudes and latitudes. This turns out to be 38.4 degrees. Remember, that's just the subtending angle that's formed between the center of the Earth station, and satellite subpoint. We still don't have elevation yet. To get that, that's step two. Calculate elevation. EL is equal to the arc cosine, just massaging the formula that I gave you on the previous page into a slightly different form. 1 plus RE over RS, quantity squared, minus 2 RE over RS, not squared, that's the cosine of gamma. If I do that, I plug the numbers into the magic calculator where everything